This module is going to cover the probability and statistics in the instrumentation and controls sections of the FE exam. So two different sections. The probability and statistics will go over just the basic types of statistics. So like estimating points and confidence intervals, expected value, sample distributions and sizes. So like mean, median, standard deviation, bell curve type of things, and goodness of fit. So correlation coefficient, like the R-squared value is that, when it's higher, it's a good fit. When it's lower, it's a bad fit. So there will be 6 to 9 questions on the quiz that are based on that. And then there will be another 4 to 6 questions on instrumentation and controls. So this covers sensors, so all of the different types of sensors that there are, data acquisition, so a lot of stuff about like frequency or analog and digital types of stuff, and then logic diagrams or programming types of things, where not that you would have to program in MATLAB or Python or something, but just the basic logic of programming, like for loops, while loops, if statements, that kind of stuff. So let's look at the handbook. So we'll go first to the probability and statistics section here and zoom in. So at the beginning, talks about the mean, median, the mode. So mean is just the mathematical term for the average value. The median is the middle value if you rank everything from lowest to highest or vice versa. Median and mean are not necessarily the same thing. And then the mode is whatever value most commonly appears. The dispersion or the range is the difference between the highest and the lowest value. So these are just the different ways to find it. And then standard deviation, variance. Standard deviation is a common one, and variance. And those just show you basically like the spread of the data and how close is the distribution to the mean. Permutations and combinations are often used with problems as far as like drawing different colors of marbles or rolling dice. Those are like, common situations of a problem. But basically the permutation is sort of like how many different objects at different times could you have. And then a combination is how many distinct combinations of objects taking a certain amount at a time. So this is n factorial over r times n minus r factorial if you're doing a combination. If you're doing a permutation, so just how many different possibilities, not necessarily how many possibilities in groups of a certain amount, you would use this first formula. And then some of these sets, just sort of know like these, like U is a union symbol, or, just kind of know that stuff. It's there if you need it. Probably not a whole lot to focus on that. But this probability function, distribution, and expected values definitely will ask you some stuff about that. So probability density function, cumulative distribution, expected value. So this is like if you have a probability of, some x being a certain value, then you want to know like, well, how likely is it to be value 1 versus value 2, etc. Combinations of random variables. So there are finding expected value, standard deviation, a binomial distribution. So this is where the probability is like how many times will you be successful in a certain number of trials. So binomial meaning like either you're successful or you're not. Not that it could be, any number of things, but it's either it is or it isn't. So it's binary. Now the normal distribution or the Gaussian distribution, this is the standard bell curve. So this is based on the mean and the standard deviation. And the main thing that you want to know here is the Z formula. So Z equals X minus mu over sigma. And there's a chart where you find the Z in the chart, and then it tells you sort of what percentile you're in. So if it asks you something about what percent of data will fall above this value or below this value, then you would use that. So here where the Z factor is that sort of number that you would look up in a table. Sigma represents the standard deviation. X is the value of the sample, and then mu is the mean of the whole thing. So you're basically comparing with the Z factor, you're trying to find out like where is that sample relative to the mean, and then dividing by the standard deviation normalizes it. So the t distribution is used when you have a smaller sample size. So you would use Z when you have a large sample, and then you would use T when you have just a small sample. Okay, so propagation of errors. Basically, if you have a bunch of different errors, they don't necessarily add up linearly or multiply together or anything like that. It really just depends on how the errors are. So you could have linear combinations of them where you just add them up. You can have measurements of uncertainty where you have to sort of square them and add them up and then take the square root. There probably won't be a whole lot on that, but there will be stuff on linear regression and goodness of fit. So this is like the least squares is basically finding the line that best fits the data and then being able to find its correlation coefficient or its error estimate. So knowing the confidence interval, this will tell you, so like when you find the intercept, how likely is it that you're correct? That's the confidence interval. And same thing for slope. But the most important thing here is the correlation coefficient, the R squared value. So basically, if your R squared is greater than like 0.9, then it's a good fit. If it's less than that, then that means your data is pretty scattered. So R is going to go between 0 and 1. So just know that a low R or a low R squared value means that you have a bad fit, and anything close to 1 means that you have a good fit. So then there are a few other little statistical things, hypothesis testing, ANOVA. Those are like generally more advanced stuff that they probably won't ask you too much about. Same thing with all of this. Yeah. It's there if you need it, but I wouldn't stress over it. Okay, so test on means of normal distribution. So if you know the variance, then basically you can find either the null hypothesis or the not null hypothesis. So basically you would be testing, okay, does your sample equal the mean or does your sample not? And that's what these sort of things are testing. And then the criteria for rejecting is, so you find the Z0 and you compare that to the Z that it gives you in the table. And then you know if it is rejected or not. If this condition is true, then it is rejected. If the condition is false, then you would not reject it. And then again, the T is done on, you'd use a T distribution here if you have a smaller sample size that like, 20 or less. So something that's not super statistically significant. So confidence intervals, here we are back with, okay, X bar being average of your population, mu being average of the global population, N being the number of items in the sample, and sigma being the standard deviation. And then the Z alpha over 2, you would find that. You would find that value and put it in, and you compare this stuff. So the test statistics set up very similar for Z versus T. The formulas look like almost identical. It just depends on how many items are in your sample set. And then if you want to find the confidence interval, then here you would just find your Z value and then look at the confidence interval, and that will tell you like, how confident are you that like, okay, 80% would mean that you're at least 80% confident that your number lies within the desired area or close, closest to that value. Okay, so these are the tables I was talking about. So you would find your X value here, and then you would go along here and see whichever one it is that you're trying to find. So like, are you trying to find how much of the population falls between plus and negative X? Are you trying to find how much of the population falls outside of plus X and minus X? or above X or below X, or just at that exact point. So in this case, you would get your X value, and then this is for a unit normal distribution. So what says X here is actually Z. So you will get that value, and then you would go over to find the probability here in this table. So meaning that if it is a probability of 1, that is 100%. And if it is a probability of 0.5, that is a 50% likelihood, and so on. So for example, if this says X is 0.0, this is the normalized version, so you would be using the Z value of this thing here. So you can calculate it on here. And then so if X is 0.0, well, this is basically like the origin. And then what this tells us here, this R of X, means that 50% of the data falls above the value of 0. So for a unit normal distribution with a mean of 0 and a standard deviation of 1, then if our X is 0.0, that is the same as the mean. And so we would know that 50% of the data would fall above that. And then if also because X is 0, then plus X and minus X are the same thing. And so 100% of the data would fall above and below, and none of it would fall inside. So that is how that works. And then this here, say if X is 1.0, so this is again the normalized average. So we're putting standard deviation at 0. And then we find X and we say, okay, if X is 1.0, well, it told us here that standard deviation is 1. So that should mean that if X is also 1, then X is 1 standard deviation above the mean. And so it would actually look like this picture that's here for the R of X. We are actually looking at this positive X value. And then coming over here, this tells us that 15.87% of the data falls above that value, which makes sense based on our knowledge of standard deviation. So now here in a student T distribution, so this is the same type of deal, but with a smaller sample size. And this tells you probability that the number that you picked is, or like what percent of the population falls above that value that you chose. And this is an F distribution, super uncommon. Yeah, okay, still that, but anyway, there if you need it. Okay, averages and range charts. So to find the average of a bunch of averages, or to find the average, you add everything up and then divide by the number of samples. So that's to find the mean. To find the average of a bunch of them, you just add up all of those averages and then divide by how many groups there were. And then this is to find the range, add them all up, divide by groups, difference between largest and smallest observations in a sample of size n. So this assumes that the groups are of equal size. So like if you have k groups that are all size of n. Standard deviation charts, you probably won't have to really do a whole lot with this stuff with the C and the U and all L and all that, but again, it's there if you need it. So test for out of control. This is something that like you would just go control F if something asks you about if you fall out of control or away from center line or whatever, just do the control F and find that section here. So these are probability density functions. Not likely that you will have questions on any of this. So know that the table is here, but most of your questions would be on a normal distribution and not necessarily on one of these other types of distributions. Although the uniform distribution is very easy. You're all familiar with uniformly distributed load, and then again, the normal distribution. So those are really the two to know. So that is it for the probability and statistics. We will go next into the instrumentation, measurement, and control. So this is different than what we just covered, but basically the first step you would want to know is types of sensors. So they goes through each of the types of sensors in the equation that is used for each one. So you can pretty much just figure out what type of sensor does the problem ask you about and then choose the appropriate formula. And something like this, so like alpha, so in this equation, R is the resistance temperature. R0 is reference at the reference temperature, which is usually like 0 degrees Celsius. T is temperature and T0 is reference. And so alpha is the expansion coefficient. And so you would actually have to either be given alpha, probably would give you alpha in the problem, or you would look it up in a table, and then you would have to find what is the resistance at this particular temperature. So then thermistors, these have their own equation. Thermocouple, you would actually have to find on the chart. So if it gives you the temperature here in degrees Fahrenheit, then knowing whatever your material is, you would follow that particular curve to whatever the temperature in Fahrenheit is, and then you would get the EMF output in millivolts. So for example, if this tells you that you have copper at 1,000 degrees Fahrenheit, then we would find 1,000 degrees. We would go up to the line that says copper, which is about here. The words are kind of covering it, but this would have an output of roughly 25 millivolts. So that's how you would calculate for that. This just talks about colors of stuff. I think the whole test is black and white, so I don't think you'll have to know that very much. A strain gauge, you may have to calculate the gauge factor, which is change in resistance over original and change in length over original. So if you know how much the size and the resistance change, you can calculate the gauge factor, or if you're given the gauge factor, you can calculate one of the other things. So if there's anything that you don't know of, just Control F and find it. So if the question asks you something about piezoelectric effect and you're like, what is that? Just Control F piezoelectric effect, it'll be right here. And then you can read about it. So remember that you don't have to have all of this stuff memorized. Now, this is just ways that you could play strain gauges if you want, different things to happen. But if it tells you like a full versus a half, these are the different ways they could be set up. So the Wheatstone bridge, you might get a problem on that. So this basically tells you that if you have the, equal ratios, then the bridge is balanced. And if you don't, then the bridge is not balanced. Ideally, you want it to be a balanced bridge. Pressure sensors, pH sensors, pretty much just plug and chug with these formulas here. Chemical sensors, they might ask you something, but probably not a whole lot. Frequency, you will have questions on sampling frequency. So you'll want to know these formulas. So basically, the sampling frequency is the inverse of the amount of time that it samples. So if something samples at 1,000 hertz, then that would be 1,000 times per second. So 0.001 seconds equals the delta T. Now the Nyquist frequency says that your sampling frequency has to be more than 2 times the Nyquist frequency. So that would be the Fn is the Nyquist and the Fs is the sampling frequency, if you want to be able to accurately make an analog signal from these discrete points. Analog to digital conversion, they've just got some formulas here. Measurement uncertainty, so they probably won't ask you a whole lot about that. Control systems, you do need to know. So for a control system, we have the input here on the left, we have the output on the right, and then this G of S is the transfer function. So the transfer function shows the impulse response function, and that is usually some equation in the S domain or the frequency domain. But the basic thing to know it is the output over the input. So G of S equals the output over the input. And then something like this here, which is a negative feedback system, this is good. You want a negative feedback system because otherwise your system will get out of control. So this is showing that, and usually this one even is a little bit more complicated than what they might give you, but we have Y being the output, we have R being the reference or the input. So the reference signal is what you want it to be. So if you have a closed loop system like this, as opposed to an open loop system like we had up here, then the actual difference between the reference and this feeded back signal from the Y would be the error. So this line right here would be called E. Error is the reference minus the actual. And this G1 is the plant. And then this L is a disturbance, which comes in as a positive because disturbances add. And then you might have another function, and then you get the output. So G1 would be the controller, and G2 would be the plant, which the plant is the actual machine that you're trying to control. The G1 is the controller, which acts on the error signal, but doesn't know what the disturbance is going to be. So that's why the disturbance shows up after the controller. So that's just stuff from, okay, negative unity feedback system. This is what you ideally want stuff to look like, where you have the reference, you have the error, you have the G, which in this case would be the controller times the plant. So you just multiply them together if they're in series, or you add them if they're in parallel, and then you get the Y. Now, steady state error for different types of input. We have these inputs here on the left. If you want a step, a ramp, or a parabola input, and then this tells you the steady state error for the type of the system, whether it's type 0, type 1, or type 2. Okay, so phase gain, phase margin, they might ask you about some of that. So be able to basically plug into these formulas. And the PID controller would have the proportional, which is this K1. They would have the integral, which is this 1 over S, which having an integral is actually not very common because it makes the math way harder. And then you would have the derivative, which this is TD times S times the K. Lag or lead compensator, they probably won't ask you about. That's a little bit more advanced, but it's just another type of compensator you can have. First order, you do need to know first order versus second order system models. So first order model has one S in the denominator. So here we have a K, which is a constant, the gain for the steady state, and then a T, or tau, which is the time constant. So this is a first order model, which basically means that if you have a step input, it will start low and it will go up like a normal exponential and eventually reach the value that you want. If you have a second order system, this one is going to oscillate normally. So we know it's second order because there's an S squared in the denominator, and it will oscillate at its damped natural frequency. So it will go up, it will go down, and it will bounce around until it settles out to the ideal value. Zeta is the damping ratio, and if zeta is greater than 1, then your second order system will look like a first order system as far as not having any oscillation. But if zeta is less than 1, it will still bounce around. The percent overshoot is what percent the signal passes up or overshoots the reference value on the first cycle. So that is it for the instrumentation, measurement, and controls. So your section here, your quiz will have 2 different sections. So there are 2 different review videos here that you can do, but I would recommend take the quiz first. If you earn less than an 80% on the quiz, then you should go back and watch these review videos and study. Remember that you can use the handbook, make full use of the handbook on your practice quiz. You can get a second chance to take it once you've taken it once, figure out the problems that you got wrong, look back through the review videos here before you take the real quiz. And once you take that real quiz, do corrections on any problems that you missed, and then upload those to this Dropbox, and that will unlock the next module here, which is chemistry and material properties.